Assalamualaikum and salam sejahtera. I'm Hidayati from University Malaysia Sabah, and today I will be presenting my research paper with title Utilization of Waste Materials in the Production of Interlocking Compressed Earth Brick. As an introduction, in general, waste material is any material that is discarded by being thrown away. In Malaysia, a high number of waste rubber tires are added annually to the existing volume, causing major challenges in terms of their disposal. The number of motor car waste tires generated annually in the country was estimated to be 8.2 million or approximately 60,000 tons per year. Annual generation of this waste will add to the existing waste stock, which are currently stockpiled and dumped in the open spaces in the countries. Most important issue with the disposal of waste tires are its long disintegration time, its shape which is capable of infestation by parasites and insects, fire hazards and resurfacing of the covered tires. So in order to reduce the amount of waste produced, one of the popular trends is to incorporate waste into the construction material. The waste rubber tires have been used in a number of civil engineering applications, such as subgrade insulation for roads, subgrade fill and embankment backfill for walls and bridge abutments, landfill in road construction, as well as raw materials for the mortar and concrete production. On the other hand, growing industry of the water treatment plant also causes increase of sludge generated from the water treatment plant. The common practice of water treatment sludge disposal in Malaysia is either discharged into the waterways or disposed to landfills. However, landfill disposal method is considered as impractical because the depletion of landfill capacity and the high cost of transportation. In addition, dumping the sludge back to the river and sanitary landfills are considered as unsustainable due to high amount of heavy metal concentration in the sludge that may harm the aquatic organism in a river. So to solve this problem, the water treatment sludge have been used in degraded soil as raw materials in the production of cement and mortar, ceramic, and they were also researched to use wastewater sludge to develop a brick. So by utilizing this waste into construction materials, the negative effect of the disposal can be reduced. However, regardless of various applications of the waste rubber tire and water treatment sludge in construction, it was noticed that their use as raw materials in the production of the interlocking compressed earth brick or ICEB is very limited. The ICEB is a type of brick which has a positive and negative frogs on the top and bottom of the brick. So this will disallow the horizontal movement. It was introduced as an alternative to conventional masonry brick in wall panels for low-rise building. The production of ICEB does not require high-skilled workers because the process is simple and convenient. It only requires 3 stages process, which starts from the soil preparation, mixing and compression, and the last stage is curing. And since the knowledge on the feasibility of both waste rubber tire and waste treatment sludge as raw materials in the ICEB production is very limited, this research aimed to investigate the possibility of using water treatment sludge and waste rubber tire as partial sand and clay soil replacement to produce the green ICEB. And specifically, the main objective of this research are to investigate the compressive strength, water absorption, and density of the ICEB produced. Next is the materials used in this research. The materials were the clay soils which obtained from the UMS site, river sand, ordinary Portland cement, water which is in the range of 10 to 15%, waste rubber tire in the form of crumb particles which was used to partially replace the soil at 5, 10 and 15% to produce the interlocking compressed rubber earth brick or ICREB, and the last one is the water treatment sludge which is used to replace the sand at 10, 30 and 50% in order to produce the interlocking compressed sludge earth brick or ICSEB. The mixed proportion of the ICREB and ICSEB bricks are shown in Table 1. And there are 3 types of testing conducted in this study. The density test, which was conducted based on the ASTM C134, Meanwhile, the compressive strength test and water absorption test, they were conducted based on the BS 3921 1985. In all ICEB bricks, they were cured for 28 days and tested at the age of 14 and 28 days of the curing. Okay, next is the results and discussion. Okay, the density of the ICREB brick is shown in figure 1. With the addition of the waste rubber tire, it can be seen that the density of the brick sample is reduced compared to the control ICEB sample. It was also noted that as the replacement percentage increased, the densities of the specimen decreased. Okay, so there is an inversely relation that can be seen between the amount of rubber replaced and the densities of the specimen. And the reasons for this is possibly due to the low specific gravity of the rubber particles, which is around 0.9 compared to the specific gravity of the clay soil, which is more than 2.6. When added into the mixtures, increase in the rubber content will increase the air content, which in turn it will reduce the unit weight of the brick samples. And another reason is possibly due to its non-polar in nature, where the rubber particles have the ability to attract and entrap large amount of air, thus reducing density of the specimen. In addition, the poor bonding between rubber particles and cement also will create voids, thus increase the brick volume and also results in density reduction. The density of the ICSEB is shown in figure 2. Similar trend was also observed for all ICSEB samples cured at 14 and 28 days period of curing. And this may be due to the sludge, which gives a higher void ratio. Hence, increase in the amount of sludge in brick will reduce the brick density. Okay, next is the compressive strength result of the ICREB, which is shown in figure 3. And based on this figure, it can be stated that all brick samples of different percentage, they are showing decrease in strength as the amount of the rubber used was increased. Only ICREB 5 was able to achieve the minimum strength as stated by the BS 3921 with 6.91 MPa at 28-day testing. And the decrease in the compressive strength of the rubberized interlocking brick was possibly due to weak bonding between the rubber particles and cement paste as compared to cement paste and natural aggregates or sand. On the other hand, the presence of rubber within the cement mortar phase has softened the matrix, hence rapid development of crack around the rubber particles while loading leads to quick failure of the specimen. Similar trend was also observed for ICSEB brick samples. Based on figure 4, it clearly shows that the compressive strength decreases as the percentage of sludge replacement increases. And this may be related to the microstructure of the ICSP. The water treatment sludge has lower fineness modulus, which is 2.45 compared to sand, which is 3.32. A low fineness modulus of the water treatment sludge has caused reduction in the density of brick, which lead to the lower compressive strength. Nevertheless, all brick samples have exceeded strength of 5 MPa, which satisfy the minimum limit of BS 3921, except for ICSEB 50, which was tested at 14 days period of curing. Okay, next is water absorption. So water absorption is one of the most significant parameters in developing good bond between brick and mortar. The water absorption results of the ICREB brick is shown in figure 5. And based on this figure, we can see that the water absorption capacities in the four mixtures, which are the control, the ICREB 5, 10 and 15% replacement, they increase with increasing percent components of the drum rubber. So these results indicate that the composite brick containing more percentage of drum rubber will absorb more water during wet curing or hydration process. And the reason for this behavior is possibly due to the existence of capillary in bricks which is filled with water. In addition, poor bonding between rubber particles and cement paste also cause the rubber-cement surface interface pressuring the water to flow around the concrete matrix. So that's why the water absorption increases as the amount of rubber in the bricks increase. And as shown in figure 6, okay, the water absorption of the ICEB bricks, they are also increased as the percentage of the clay replacement increase. And this is possibly due to high water absorption of sludge compared to sand, which result in increase of the brick porosity and finally cause high water absorption value compared to the control brick. Based on the results obtained on the density, compressive strength, and water absorption, the feasibility of using both waste rubber tires and water treatment sludge in the interlocking compressed brick, they are compared based on the standard requirement of ASTM and BS standard. In accordance with the ASTM C90, the concrete masonry units, they are classified into 3 different categories based on the oven dry unit weight. And these categories are light weight, medium weight, and normal weight. And according to BS 3921 1985, the minimum compressive strength for brick is 5 MPa. Meanwhile, the water absorption limit is specified that for engineering A and B, the water absorption is less or equal than 4.5%. For dam-proof coast brick, the absorption is less or equal than 7%. Meanwhile, bricks for all other classes or application than those mentioned above, they are not restricted to any water absorption limit. Therefore, based on the results and standard of requirement, it is concluded that the ICREB and ICSEB brick samples can be categorized as lightweight bricks with density of less than 1680 kg per cubic meter, and this result is favorable for easy handling and transportation, which save fuel and energy. And the addition of rubber crown leads to the undesirable reduction in the compressive strength of the ICREB. Results showed that the ICREB 5 they satisfies the minimum requirement with strength of 6.91 MPa at 28 days curing. Hence, to produce good compressive strength of rubberized ICEB, 5% replacement of clay by waste rubber tire is appropriate. And partial replacement of sand with 10 to 50% of water treatment sludge had produced ICEB with good compressive strength, which satisfies the minimum strength requirement as stated in the BS 3921, which is a minimum of 5 MPa. And 50% of sand replacement by water treatment sludge can be considered as appropriate percentage for the ICEB production. This would lead to lower production costs besides minimizing environmental impacts due to the sludge disposal. The last one is the water absorption of all ICREB and ICSEB samples. They are acceptable within the class of all other classes with range of 7.2 to 19.2%. So with that, okay, I end my presentation and thank you.